Let me introduce our speaker today. So it's a great pleasure to host Deniz Altınbüken. Deniz is a senior software engineer in the Learned Systems team at Google Brain Research. She received her PhD in computer science from Cornell University in 2017, specializing on distributed systems, consensus protocols, and self-adapting systems. Since her PhD, Deniz has worked on large-scale database systems and learned systems. And currently she is focusing on improving the state of the art in systems using machine learning and mainly on caching and indexing. Her work has appeared in top conferences and workshops, including SOSP and ML for Systems at NeurIPS. Deniz is also a graduate of our BS program in computer engineering. So thank you, Deniz, for accepting our invitation. And the floor is yours.
Thank you, my pleasure. Thank you for the opportunity to give a talk. So today, and thank you for the introduction. So today I'm going to talk about my experiences and some of our projects about ML for systems. And this is joint work with a lot of collaborators. So for Learned Systems team, we are a team of like 8 and 9 people. And in Learned Index, which is one of the projects that I'm going to talk about today, we are also a large group of people working on this. First, let me start by why I named this talk The Tip of the Iceberg. So when working with machine learning in systems, machine learning is great for finding patterns in data, and it can be a really, really powerful tool. And it is really great to be able to use it to solve systems problems. And with it comes some hidden joys. So when you use machine learning, you can find some patterns that you didn't know existed, or you can find some hidden optimizations. So you start a project thinking, oh, we will get some efficiency from this or some gains. And then sometimes you get way more than you anticipated, and it's amazing. On the flip side, though, there are also hidden challenges. So using ML in systems is very complicated most of the time. It is really intricate because systems are very complicated, and it's much more involved than just training a model and making a decision. So very much like an iceberg, you might start a project thinking, oh, it's like this much work, but then as you are in it, you really realize there's this whole hidden part that you did not anticipate, which makes things very difficult. So that's why generally when I'm working on these projects, I feel like, or I also remind myself and everyone I work with, it's kind of like an iceberg, like there's a lot of hidden stuff that will come out, so be prepared. So the talk today is, first, I'm going to generally talk about ML for systems. So what it is, or what kinds of things that we use machine learning in systems, how we design these solutions from a kind of high level. If needed, and if we have time, I have some extra slides that we might go into later. Then I'm going to talk about the Learned Index project, which is one of our projects. First, the general Learned Index idea, and then how we applied it to a specific database, which is Bigtable at Google. So let me start with ML for systems. So there are 2 ways to talk about ML for systems. One is you can think of it as replacing heuristics with learned patterns. What that means is heuristics are generally when we build systems or any type of complicated program, you kind of end up having rules that have been decided or algorithms that you basically implement. Some of these things can be, for example, you make some rules about which data gets cached. So you have some algorithms, which is like the caching algorithms, and then you implement or code some common sense wisdom, and then that becomes the heuristic. And with the machine learning for systems projects, what we intend to do is let's take these heuristics that people who are experts or who are good have implemented and see if we actually learn from the environment or how the system is working, if we can do better. So instead of saying in the cache, let's use the least recently used, let's just keep the least recently used stuff out of the cache, could we actually implement something more complicated that looks at past usage and makes some smarter caching choices? Another way of talking or thinking about ML for systems that I've seen is using data-driven approaches in the implementation of a system policy. So what that means is system policies that are, again, rules or how a system works, and then can we replace them with data-driven ways? So they are very similar, but there's a little bit of difference because in the second way of thinking about it, there's this policy that comes, which are like how the system is implemented, how the decisions are made. So there are many examples at this point. So while this is kind of a new field, so it's maybe like 5 years old, there are a lot of applications and it's growing. Some good examples are in database and storage systems. You can make decisions using machine learning about how to execute a read query. So a read goes to a database, and there is a lot of ways to search the whole database and get the answers. So how do you order these searches and sorts and all these kinds of operations? You can make these decisions using machine learning. You can make the decision about when to write to disk, if you have a storage system where when the memory is full, you're flashing to disk. You can make that decision using machine learning about timing. I've seen examples of decisions about where to store the data. So if you have a replicated system, you choose where data is stored. So it can be closer to users. It can be stored in ways that makes failure happening at the same time least likely, and there are a bunch of different ways, and you can use machine learning to pick optimal places. How to index the data, which is the one that I'm going to talk about today. Data is laid out in various ways, and through machine learning, you can find patterns and maybe make indexing easier. And again, another example I mentioned is like which data to keep in the cache. That's a good one. So these are for like database and storage ones. Another field that ML for systems is being used a lot is data center management. So it's a very complicated problem. You can decide how to route traffic, which data to cache again in CDNs, and how to detect failures in these complicated places. A really cool one that is right now going on in my larger team is normally chip design, where dies on the chip are laid out. This is a problem that is generally dealt with by experts that spend a lot of hours. So now there are projects that use reinforcement learning to design chips, basically making how the hardware decisions using machine learning. That is very interesting. In compiler optimization, if there are students here who are taking like compiler class, there are a lot of decisions we make about like which registers to allocate, which ones to use, how to tune the heuristics in compiler. All that can be made in using machine learning. And the last one is like cluster management, which is again, like you have a huge data center and now you have to decide how to run programs and jobs. You can make scheduling decisions, optimizations, all these things using machine learning. So these are a bunch of examples of how these projects are used or how machine learning is used. And as you can see, these are very complicated problems. They're not very trivial. And there are many different ways of solving these problems. So and it's not really, there's not a really recipe when you want to implement a solution. So you start a problem saying, let's say caching, you want to say, okay, let's see which objects to cache in like more frequently and which ones to evict. You can use reinforcement learning. You can reward better decisions and punish bad ones, and observe the state of the system and change it and repeat. So that would be a way to solve the problem using reinforcement learning. The same problem you could solve using supervised learning, which is you can have a lot of inputs that you might use a simulator, then you get a lot of basically results how the system behaves. You pick the best outputs, and then you have this bulk of knowledge that you can use always to train models. Or you can do an unsupervised learning approach. You can look at the data that like you have logs, you have all the system state, how things are behaving, but how efficient things are. And you can try to find patterns, which is like, oh, if we cache this type of object, then this happens. So that, like you might see or find these kinds of patterns through clustering and association of events. So there are many different ways of solving these problems. As a result, it's good to kind of sometimes have like kind of like recipes in mind about like how to tackle problems. So one example of that is for problems that are optimization type problems, which is find the best way to do this or find the best algorithm or stuff like this. The way generally these kinds of solutions work is you have a deployed system. So there's a system that is already working. It can be a cluster management software, data center management software, database, any type of system. Generally, all these are large-scale distributed systems. You have deployed system. So then you have a lot of information that you can gather, which is basically states that you're recording. So you can record logs, you can record how efficient things are, you can record how data is being accessed, what is read, what is written, many different types of things. And you can use this information to learn a model. There's not one recipe for learning a model. As I said, there are many different ways of doing this. I won't go into detail, but if you are interested, we can talk about it in the end of the talk. And then you can use these models that you had trained to make the decisions in the system, which kind of feeds back again to the system and changes the system state. And then basically you have this kind of like a pipeline, very similar to like how you use machine learning. You build this pipeline of a system, you observe, collect data, train models, then you change the state and you just continue. So this is, of course, a very high level and simplified way. Another common thing that happens in ML for systems is actually how finding patterns in data. So there's a deployed system, and there are many different parts of the systems that are just like components like an index. And you can identify a data structure or some component that basically stores data or kind of encapsulates some kind of information. So then you actually learn a model instead of like storing this large data structures or information capsules. You can learn a model to see like or to store patterns in a more efficient way, and then use it to basically as a component in the system. And this is a new way of basically thinking about systems where you take a component, like for example, the index or the part that routes traffic, like a controller, and you completely just replace it with a machine learning model. And that's another way we basically do ML for systems problems. Do we have any questions until here? Also, I forgot to mention in the beginning of the talk, if you have questions, just you can interrupt me. Yeah.
I have a question, Deniz.
Yeah.
Identifying the data structure part, for example, from your indexing domain, what does it correspond to?
Yeah, so one way of thinking about it is, which I'll go into detail, but let me just talk about it in a very high level way now, is in indexing, for example, indexes are used to find data. So it's kind of like exactly like the index of a book. So we, and I think like everyone who have taken the data structures class would remember these kinds of things. So you have this efficient way of kind of like going down a tree, and then the trees like point to parts in data. Essentially, if you look at how this index is working, it's storing information. It's a way to efficiently store information. And the machine learning approach is saying that instead of storing it in a data structure, could we store it in a model? Because a model also keeps, basically stores data, but in the form of a mathematical function. So that's the way of kind of thinking about that. Yeah. Okay, I'll continue. So before I go into the more tangible example, I wanted to highlight the challenges in a more detailed way. So the biggest challenges in ML4 systems are coming from the system side. And of course, there's a lot of complexity with the machine learning side too. But generally at this point, a lot of the machine learning that is being used is more on the simpler side, because that is not the more difficult part is like the integration of like machine learning into systems. So you don't really need extremely smart models. But the difficulty comes with the fact that systems that we deal with are generally very, very complex. They rely on complex algorithms and implementations. So if you imagine a database, at this point, like every database is distributed. There are many different replicas of data. You have to keep everything copied 10 times over. There might be failures that you have to deal with. There are different kinds of data probably that you have to store in terms of types. So the systems themselves are very complex, and there are many components in these systems that work together. So when you change something in the system, it affects a lot of other components, and the environments that they are deployed in, like data centers or the cloud environments, are also very complex. So changes again have many different effects, and if you train a model to work well, it is not really guaranteed to work well over time, because things change, system changes. So you have to have these models that generalize. So it gets a lot of complexity from those. The other part, which is connecting to what I said about the models that need to evolve, systems evolve and change over time. So requirements might change, the workloads change, the environment that they are deployed in changes over time, even the hardware that the code is running changes. So in terms of like when you think about integrating machine learning, then it becomes really complex, because you have a machine learning algorithm. In a lot of cases, it might be a black box. So you might not really understand why it's suggesting something. It might suggest things that are good sometimes, but for other times they're not. So you need to deal with understandability, being able to debug when things go bad. So there are a lot of challenges that come with that too. And the last part is all this is very, very expensive. So running systems are already expensive. There's a lot of bandwidth that is used, a lot of CPUs, SSDs or RAM. At this point, store so much data in general, you pay for those. When you add machine learning to this, then you add even more resource consumption, because you need to like store even more data. You have to process the data. You have to train all these models 10 times over. You have to keep training. It gets very expensive and very time intensive as well. And the last part is a very challenging thing is expertise is very important. So when you have a complex database, there are people who built it, who deploy it, who run it. And with the machine learning components as well, you need to have people who understand this integration and have to debug it when things go wrong. So you add even more, like you now require more expertise even in like dealing with systems. So these are the really challenging parts about ML4 systems. So as a result, when we do projects, we have to be going very with baby steps. As I said, like we don't really at this point use very complex machine learning algorithms because they become extremely hard to debug. They become very expensive. And so you generally start very small and now you grow. Okay, so a lot of the things I said were a little like high level and more like broad. So now I will start talking about one of our projects, which is a very tangible example. This is the Learned Index project. So the learned indexes are basically the main idea behind it is a model can learn the structure of lookup keys and use this learned pattern to effectively predict the position of records, which is an index. So what does that mean? It's kind of like a complex sentence. The main idea is we have here on the left-hand side an index, which is the traditional one, which is a B tree. So the job of an index is you have all this data that is stored in a, let's say, an array, and you want to find, given a key, a value that is somewhere in this array. So a very naive way of doing that is you start at the beginning of the array and now you search for the value you want. But that is very inefficient. So over time, because people don't want to search a database or a storage system, like starting from the beginning and go through everything to find a value to read, they came up with the idea that there's a key for a value, and then we will use this key to index it and then find it in the array. So the trees, which is like a B tree index, you give it a key and then it points you through going down the tree to a position in the array. And then generally they are in page granularity. So you go here and then you search within here instead of searching the whole array. So that's the main idea behind an index. And a learned index, the main idea here is that instead of having a tree, can we have a machine learning model, which given a key, gives you a position again in the array. So it's doing exactly the same thing, but using a model instead of a tree. So here for efficiency, the B trees, as I said, index into a page. And then in the model, because machine learning is never accurate, you index with an error, and now you can search there. Very similar idea. Does this make sense in terms of like how the learned index works? Or are there any questions?
Yeah, in fact, Deniz, I mean, this is quite interesting. I envision that actually, I mean, some professors, for example, the elderly ones, they stack lots of papers in the office, and whenever you ask something, they get up and find actually whatever they are looking for. So
yeah, that's like they have a B tree in their brain.
Yeah, they have a B tree, or maybe they have a neural network actually, which learned the position of what they are looking for.
Yeah, exactly. Yeah, it's a very similar idea. Yeah. So this is the main idea behind learned index. So replace the tree with a model. Why is this cool or interesting, or why would we want to do this? The reason is the trees are very large generally because you store all these keys in the tree. So here it's like a triangle, but in reality it's like many layers of a tree. A model is a mathematical function, so it's just kind of like a couple of integers. So in terms of like in really large databases, the B tree could be shrinking from gigabytes of data to a couple kilobytes. And as a result, you can always keep it in memory instead of like having to read it from disk. So it has all these kinds of advantages in terms of efficiency. So this paper came out in 2018. And it was a more machine learning paper, and all the results were simulated. And I'm a systems person, so looking at that, we were questioning, okay, that's cool, but is that actually going to work in a system? Because if you simulate data, that's not really a system. So that's where the Bigtable Learned Index project comes in, which is Bigtable is one of the largest databases at Google. So it stores a lot of data. We have large indexes. So we said, could we replace the indexes with learned indexes? And so to talk about Bigtable Learned Index, I'll talk about SS tables first, because that's the way data is stored. So the SS tables are SS stands for sorted strings, and it's basically a file which is just a bunch of string type, and then everything is a key value pair, and they are sorted by the key. So that's it. So you just sort all the data, write it to disk. So the main idea is that as you're writing to Bigtable, which is the database, first things go into memory. Then when the memory gets full, you say, okay, I can't write to memory anymore. I have to write things to disk, flash. While doing that, you take the stuff in memory, you sort them into string files, and then you write them to disk. These files that will be written to disk, they are large. So they are like gigabytes, sometimes probably terabytes. So you need an index. When you read them, you don't want to just go through the whole file like line by line. And that's where the indexes come in. So these SS tables that are used extensively at Google, not just at Bigtable, but especially in Bigtable, use these B trees for indexing. So this was a great match. And then that's why we said, okay, let's replace these indexes with the learned index. So this project was really a story of surprises. So we started with really cool expectations, which is like, oh, we'll just use the same ideas and it will just work. So we collaborated with the authors, and we were like, oh, the B trees are large, so they will shrink and it will be really fast, and we will keep everything in the memory. We anticipated that the index sizes will reduce significantly. There will be fewer disk accesses because now we can keep the index in memory, and it will be great for tail latency. The reason is tail latency is basically a lot of files that are really large, or files that are not really read often, they end up on disk. So all these random reads that like someone opens a weird, obscure YouTube video that nobody opened for like months. So that goes to disk somewhere, and that is slow. So if you could improve that a little bit, then instead of like reading the index from disk, you read from memory, then it's faster. So that's what the tail latency expectations were coming from. In reality, though, as we worked on this project, we couldn't use a lot of the ideas in the original paper because they were performance prohibitive, because when you have an actual system, things have to be extremely fast. So I'll go into details of those a little bit. Index ended up to being small, but it was bigger than originally thought. And the reason is, in real systems, you keep a lot of things, which is like you have to keep not just the key value, but you keep information about how the data is encrypted. You keep information about how the data is laid out, so that you can keep some statistics to export, and a bunch of different like metadata that you have to keep, which are also in the index. So we had to maintain those. And we realized, though, in the end, we still had a lot of wins, and that these came from when we write to disk and read from disk, everything is compressed and decompressed. And that is also very expensive. So whenever we do not write to disk, we save a lot by not compressing or decompressing. And the other part was there, the interaction between, which is never, of course, in the original paper, there's a lot of interaction with the prefetcher, which when you read from disk, it doesn't just like load, there's a prefetcher in between, and we could basically get rid of all the stuff that the prefetcher has to do. So it was also much faster as a result of this. So while this is a lot of information, the main takeaway here is that when you actually implement these things, like the ideas in the systems themselves, they get much more complicated. And very much like an iceberg, you see, like things change, and now you realize that there are a lot of hidden things that you didn't think about that come up, which are sometimes exciting and sometimes extremely frustrating. Okay, so let me check time. Yeah, sorry, this way. Okay, yeah, I have about 15 minutes. Great. So let's talk about how the mechanism works. So the main challenges that we had to deal with is in the learned index, I said that you could train a model and then it learns like min and max error. So then you can search, but so then the model can actually make some incorrect predictions, and it's still fine because you can search a little bit. In reality, though, these incorrect predictions require that the correct location is searched. And in a system like Bigtable, which we go to disk a lot, that was very prohibitive. So we could not do that. We had to basically change the way that we learned. Oh, sorry. And so the cool thing that we did there is we, before writing to disk, we go through the data, we learn the whole layout, and then we write according to the index. I'll go into detail of how that works. This is a little vague now. And the other part is, of course, as I said, Bigtable is very complex. So we had to deal with like prefetching, special keys, blocks that are empty. Blocks are like parts of the file that are very empty or very large, the data being very skewed, all these things that we have to deal with. And the contributions of this work in the end, though, was that we managed to have the first design of learned index for a working production level system, which was Bigtable. We had a new learned index model design for string keys with guarantees about like monotonicity, which is the keys are always like increasing. And the evaluation of our solution demonstrated that using learned index improves, especially read performance. So how does this work? So indexing in disk-based systems here, the main idea is, again, you give the key, the index basically routes you to a block, which is how data is written in these disk-based systems, like into blocks. And through using the index, you lower the search that you have to do during a read. Indexes return the location of a value given a key, and the traditional indexes use data structures like B-trees. In the learned index, we train a learned CDF model, and we achieve higher lookup times, and then this model is much smaller. And the model is trained during writes. The way that works is, so this is how an SS table looks, which is the file that we end up writing to disk. So this is a sorted string table. If you look at the right-hand side, there are blocks of data and then blocks of indexes, index parts. When we are writing, we create this file and then write to disk. And I'll go through how we do that to detail it. And the data is written in these data blocks, then we create these index blocks, and then we create this footer in the end and then write. So The way this works with a two-level index, which is the default in Bigtable, is we have, let's say, this data block here, which we start writing key 1 and value A as like values. And then as we continue writing all these like sorted data, at some point the data block gets full. So then this is the part when we say, okay, this data block is full, write it to the index, which is key 3, like key 3, anything before key 3 is residing in data block that is 1. So this is how we built the traditional index. So then as we continue writing, so we write to data block 2, if that gets full, we say, okay, everything between key 3 and 5 is in data block 2. And then this, when this index block gets full, we write the information about this index block into a level 0 index block, which is like a level in the tree. We say that everything before key 5 level 1 I block is in here in the first one. So we continue basically writing all the data blocks and the index blocks. And then at some point they're all written and then the file gets full. And then we at the footer write where the index is. And then this is how we create a traditional B tree index in an SS table and how we write files. So when we are reading them, we get a key. So someone asks for basically key 3, give me the value for key 3. So you basically go to, with the key 3 in your hand, you load this file, the footer points you to level 0. It says key 3 is smaller than key 5, so you go to level 1. Here you have key 3, so you know that it's in data block 1, so you go to data block 1, and now you find it here. So this is how the read works now. With the learned index, we don't write the data blocks. We don't write an index. What we do is we go through the data that will be written to data blocks, and then we train a model which learns given a key where the data block offsets are. So which is like which data block it is residing in. And we have this function in our hand. And then we use this function to say, to write the data, which is data block 1 will have key 1, key 2, key 3, and then data block 2 has key 4, key 5. So basically this function, you say key 1, and then it tells you, okay, data block 1, so you write it according to that. You give key 2, it says data block 1, you write it again here. So you use the function to write. And then during, so very similar to the other index, you finalize with footer. So the whole file is written. And then during reads, again, let's say I'm looking for key 3. I use this function, I say key 3, it gives me key 3 data block 1. So then I just go to here. So I didn't have to go through any index blocks like I had to do with the B3 index. I didn't have to search for it really. I just looked it up from the function. So that's that kind of like how the learned index works. And then there's the main idea here is that we are not really iterating through any index entries, not comparing any keys anymore, and not loading these index blocks. And we're just like doing a mathematical lookup. So it's much, much faster. So I will go to even more detail on like how this is mathematically working to really show you. So another way of thinking of how this data is laid out is there is a key space, which is like the x-axis here. So we have, let's say, key 1, 2, 3, 4, 5, 6, 7. And they are basically residing in different offsets in the block, in the file. And there are and these correspond to different data blocks. So let's say this is data offset 100. Anything before 100 is in the first data block. Anything before 200 and between like 100 and 200 are in data block 2. So this is how we basically build the index. So in the when we train a model, we get these keys and then these starting offsets, and then we build this function. So something like this. We say, okay, I'm learning where these like the X values are, and then what the corresponding offsets are. So you basically build this model, which is a function to try to approximate it, but it's not perfect because machine learning is never perfect. So you get this line. So the way that we write then is we say, okay, this model tells us that given a key, the offset will be here. So for key 1, we just write it to this offset. So this is how we basically create the index using the function. So then when it's time to store the index, these are only the points that we have in our hand, and then we can store those. And then to read, we have the function. When we get a key in our hand, let's say key 2 or key 3, given the key 3, it says the starting offset is like 150 or something, which is in data block 2. So you basically read from there. So it's like you just have this function, and then given an X value, it gives you the Y value. So that's the mathematical way of showing the same thing. Are there any questions?
I have a question.
Sure.
For the presentation.
Yeah.
You said replacing B3 with machine learning models decrease the size.
Mm-hmm.
This is the first benefit, and also it makes it easy to find the index. This is the second. Which benefit is more significant in this problem?
Yeah. In the end, the size, I think, became more significant. The reason is when things are small, or like something like an index is small, you can always keep it in memory because the size difference is between a couple gigabytes and a kilobyte. So when you can keep things in memory, you really save a lot by not having to read it from disk. And that comes with, you save the time to read from disk. You save, as I mentioned, the compression you had to do when you write to disk. And then the decompression you have to do when you read from disk. So there are a lot of things that come from not having to go through this. So the size is the most important one. Yeah.
Okay, thank you very much.
Of course. Yeah. So yeah, in the read, basically given a key, then we can get the value, and then the index becomes just this very simple function. So the results of using this index, then we looked into both latency and throughput. So for latency, the main idea is when we do a point lookup, which is a read for just one key, how long does it take to do that read and come back? So that's the latency. And on average, so in the 99th percentile, which means for the 99% of the operations, we reduced that latency by 38% for when you do a single key lookup. And for scans, which is basically reads that you give a lot of, like you do key 1, key 2, key 3, key 4, like you scan through the data. For those, there was not that much of a gain. The reason is when you do a scan, for the first read, you load the index from disk to memory. But then for all the other consecutives, which is like key 2, key 3, key 4, key 5, the index is already in memory, so you don't really pay for it anymore. As a result, we don't really save anything by not reading from disk over time. So if you do like 1,000 reads, then over time that gain disappears for 99% of the operations. And the mean latency, was reduced 36% for point lookups and 22% for scans. So on the mean, it is a little more because this includes different kinds of operations as well. So this is also related to the last question, which is the main idea here. The learned index eliminates the need for disk accesses, and which improves this latency. And the other one is throughput, which is how fast can we do a lot of reads and then a lot of scans. For throughput, the numbers are even higher. So for point lookups, 54% and 56% improvement in the 99th percentile, which is great for basically tail latency. And in the mean values, it's 55% for point lookups and 28% for scans. So the reason throughput is so much better is the other thing that I mentioned, which is the compression and decompression. So the way of thinking about this is when we are reading from disk, the compression is or decompression, I guess, is the more important part. Decompression is very resource intensive. You are using the CPU to do a lot of work. And as a result, it becomes a bottleneck. So when you have to decompress, you can't do things fast anymore because you're like stuck on waiting for it. And that's why when you get rid of it, now you can improve throughput, which is how fast things can go. As we are accessing fewer index blocks, then like we can really improve this, like kind of like remove that bottleneck, and then things can go really, really fast. So that's the main idea. Okay, so the main insights in this project, or like how we applied learned indexes to Bigtable is, so the learned index is used to dictate how the data is laid out. So we basically train this like function I showed, which is the line, and then we use that to write the data. So the learned index is always correct. So we never search for the data. We just learn that and then write the data according to it, which was great and needed for a system like Bigtable. Index seek time is constant. In the past, depending on how deep you have to go in the tree, you might need to seek and load a bunch of index blocks. Now that's gone. You just always use the function. For really large files, this is especially important because you don't have to load these really large index files. And learned index size is smaller, which helps basically keep it in memory. And it eliminates discretes, and this reduces tail latency, especially again for large tables. Let me see how much time I have. I have about 10 minutes. Are there any other questions? If not, I have some extra slides that I can go into a little bit. But let's wait a couple seconds.
Let me ask a question, Deniz. In your experiments, so the data is like stored at a single centralized node, or
no,
you also consider distribution aspects?
Yeah, these are distributed. So we run them on multiple machines, and we write in the experiments terabytes of data, and then force them to be written to disk. And then as far as I remember, I think we had 1,000 servers, and then they are on different machines. I think they might not be very far away from each other. So it's not like one is in Europe, another one is in the US, and another one is in India. So they are, I think, in a similar, like a closed data center, like in one single data center, but 1,000 machines on different like racks. Yeah.
So did you deploy this solution? Like, are you using it real?
Yeah, so it is in the process of getting into production. So there are a lot of things that need to be, which has been done. So like all the edge cases need to be done and things like this. So in some parts of production that it is being used, but it's not 100% yet. Yeah.
Okay, thank you. Are there any other questions from the audience? Okay.
Okay. So my conclusion is very short. It is exactly what I talked about in the beginning, which is machine learning is great in finding patterns in data, and it can be a very powerful tool, but it comes with these hidden joys and challenges. Joys is in this learned index example is all this decompression and compression costs that we didn't even think about, and all these throughput improvements that we really didn't even anticipate. We got a lot of those, and that was great. The challenges were, of course, we had to deal with a lot of edge cases. Some things I didn't mention here is when data is really skewed, which is sometimes the case, this function gets really funky. So then you get like it can suggest very different values, and then you can get really, really large data blocks where parts of it are empty and things like this. So we had to resolve a lot of edge case scenarios and things like that. Since I have a couple more minutes, let's see again, about 8, I had some extra slides that I can go into. Let me go there. Yeah, so this is another, this is again, about ML4 systems. We have other projects that we work on. So caching is an example. The main idea behind caching problems is we ask the question of which block should we evict when you are like accessing the cache and it's full. Now we have to make a decision about which block to evict. Can we do that using machine learning? Or for compiler optimization, we ask questions around like which registers to allocate. And with these kinds of projects, there are generally 6 things that we actually worked on creating this like recipes or the 6 points. Like whenever we start an ML4 systems project, we go through this like 6 things, and we are very careful about these. And the first one is like understanding the constraints, which is, okay, you want to solve a problem, let's say the caching. What are the constraints that you have? That really helps you think about, can I even use machine learning? Should I be using machine learning? If I'm using machine learning, what can I do? And things like this. And the second one is quantifying the headroom. Just because you can apply machine learning to a problem doesn't mean that it will improve anything, because maybe it is already really, really improved. So for those, whenever we start a project, we actually do this analysis, which is in the caching example, it's like we deploy like a Oracle cache, which is called, for example, the Blady algorithm. You say, if we made all these caching decisions optimally, how much improvement would it be? And how it is today with the algorithms that we have. Let's say we find that there's a 20% improvement potential. Then we look into, okay, how much of that can we actually achieve with machine learning? So we have to kind of like simulate or try to like have a prototypey type of implementation to see, is this gonna work? Then we justify the project, because if you're not really gonna get that much, you can't really justify all this work. So that's very important, to quantifying the headroom. The third one is we start always very, very small and very, very simple. We don't jump into like neural network because those get more like expensive, really large. You have to make a lot of decisions, a lot of tuning and stuff. We start with very small stuff like decision trees, sometimes just like a CDF model. and things like that. The fourth thing is we always have to think about the overheads with machine learning. So when you use machine learning, you are paying for training the model. But there is another one, which is whenever you have a trained model, even looking up or asking the model for something might be very expensive. If you have a very complicated network, just like inputting something and getting an output might be costing a couple milliseconds. And sometimes you don't even have those milliseconds. So that's another thing that we always have to think about. The fifth one is, this is very interesting. So understanding what the model is doing is important to a level, but we always also try to stay realistic, which is sometimes with heuristics, also you don't understand how things are working. So especially I think compilers is a good example. There are a lot of heuristics that are in compilers that over time people just try different things, and then some things were better, and sometimes it's not even known why that is better, and then you just accept it. So in machine learning too, it sometimes happens, but you still have to have a good understanding to be able to debug when things go wrong. So it's very important to have these simpler models that you can understand or reason about. And the sixth one, which is really important, is one thing we realized is because systems are deployed for very long amounts of time, like you deploy it, it works for years. And they also get updated all the time. You like always work on the systems, evolve them. We need to train the models to generalize. So we do a lot of work on this, which is when it comes to, for example, learning with data, we collect data not for one day, but over the course of months, years, including like special days, like weekends, weekdays, holidays, all these, so that you can like detect the behavior changes and all types of stuff. So you really have to think about all these like edge cases of like generalization. Yeah, so these six things are like kind of like the pillars that we always think about and always go back to make sure that the project makes sense, it is successful, and it's working. Yeah. Let me go back to here. Yeah, so thank you so much. I hope this was useful. If you have any other questions.
Thank you, Deniz. Thank you very much once again. I know that it is midnight at your side.
That's
thank you
completely
for
fine. Yeah.
accepting our invitation. Are there any other questions before we conclude?
So Deniz, maybe as a last comment, should we expect actually learned operating systems at a point which will adapt to needs of the users and the resources of the system?
I think in the long run, I suspect there will be a balance, which is for systems, some things will be done with machine learning and some things will be done with just the old heuristic way of like, there is an algorithm and that's how it's working. But I am expecting a lot of the systems to get smarter over time, just because it makes sense in many aspects, like they will get cheaper. You will remove human involvement more and more, which is more desirable. So eventually I think we are going to get like smarter systems that are like adapting and more able to adjust to different things. Yeah.
Thank you again.
Of course. Yeah. Thank you again. Yeah.
Thank you, Deniz.